Hi everyone. So now I am welcoming our India speaker, Anu. So she is a fourth year PhD student at IIT BHU Physics Department, and she is working with Vidya Vinay Karak, our Vidyada, and she will be and she will be speaking about her research on bipolar magnetic regions, which is abbreviated at BMR. So it will be a statistical analysis, and from there we can know about the flux rope model using her research methods. So please welcome Anu. So the stage is yours.
Thank you so much. First of all, let me start by thanking the organizers for inviting me to give this talk, and thank you, Devesh, for this good introduction. So as he already said, I am Anu Sreedevi. I am working in Department of Physics, IIT BHU, with Dr. Vidya Karak. And last 2 years, I'm in my fourth year of my PhD, and this has been my work since I finished my coursework. So this is what I have been doing. I have been studying the BMR evolution, the bipolar, as he said, bipolar magnetic region evolution. So this is this is something that I'm very passionate about, and this is one of my first project when I joined my PhD. So let's start with some introduction. So bipolar magnetic region, I don't think I have to talk much about, like, in white light images, you see sunspots, but and they usually appear in pairs. If you look at the same in the line of sight magnetogram observation, you will see that the sunspot pair as polarities of much more general feature, which is called as bipolar magnetic regions, which we are calling BMRs in short. And usually they form tilted, they don't form in parallel with equator, they form a little bit tilted, which is called as tilt angle. And this verified by various previous researchers using the data from various observatories, that higher latitude forming BMRs will have a higher tilt, which is the famous Joyce law, which was proposed by Hale et al. In 1990. And this tilt is very crucial in the Babcock-Gleiton process, where the BMRs evolve and disperse, and the dispersed flux is taken up to poles by the meridional, the local flows to cause the polarity reversal and create the polar field for the next cycle. So the people who study sunspots, or the people who study solar dynamo, for them tilt is a very interesting and very crucial very crucial part of their study. So here again I am trying to attempt the study, or the BMR evolution study, using the tilt statistics. Now there is still confusion of how BMRs are formed. So one of the simplest explanation is given by thin flux tube model. So thin flux tube model says that there is a bundle of magnetic field lines, which we will be calling as thin flux tube. They will be anchored at the convection zone, and due to magnetic buoyancy, they will rise up through the convection zone, and the flux tube pierces out of the photosphere, which we will see as flux emergence, and eventually which will become as sunspot on the photosphere. Now, as the flux tube rises, there will be draining plasma, and that draining plasma will be subjected to Coriolis force, and that will cause a tilt in these observed regions. And this was proposed by De Silva Chaudhary in 1993. Being a very since it was proposed, there was a lot of simulation studies that happened using this thin flux tube assumption, and one of the famous one is by Fan et al. 1994, where she and her group gave an empirical relation for the tilt in the BMRs with the properties of the BMR. We will come back to this in a later phase. So this is just a you can say promo, but we will come back with slide later time. Now, my motivation why I started the study is that I wanted to understand how the BMRs evolve and their impact on the solar dynamo and the long-term variation of the sun. So we will be looking at the magnetic aspect, morphological aspect of the evolution of the BMRs, and in the later study, I'll be checking if the thin flux tube model is still a viable theory for explaining the formation of the BMR. Now, how did we do this? So we didn't have much catalogs available giving the information of evolutionary information of individual BMRs. So we just went ahead and developed an automatic algorithm for tracking the BMRs. And we are calling it AutoTAB. And AutoTAB has created a catalog of almost 12,173 individual BMRs with evolutionary information of each of these BMRs. And we use this catalog to study, to look for the observational signatures of thin flux tube model. So my talk will be divided in two parts. I thought that some people will be interested at least in the working of the algorithm, and some people will also be interested in science. So I have made the talk in two sections. So let's get to the algorithm. But before that, I have been talking a lot about tracking the BMRs and the evolutionary dynamics and all those words I have used. But the first question we should ask is, why do we need to track the BMRs? So the answer is, most of the things that we know about sunspot or for the dynamo, the observational signatures of dynamo, observation supports of the working of the dynamo is through sunspot studies, and it has been an intriguing subject since the time we started looking at sunspots. So most of the statistical studies regarding with the tilt or with the flux, it has been conducted by considering without tracking into consideration. So by which I mean that if I observe one sunspot today, I'll consider it as a new sunspot, and the same sunspot will be appearing tomorrow also. So the sunspot that's appearing tomorrow again in my statistics will be taken as a new sunspot. So we all know that bigger active regions, bigger sunspot will live for a longer lifetime. So in your statistics, in your data, the longer living BMRs will have a much higher weightage. So this may skew your analysis to the characteristics of bigger and longer living BMRs. So we need to avoid that, and that's why we took up tracking as in our consideration and into our data set and into our studies. Now let's get into tracking. But before that, track something, we need to detect something. So let me just give a brief explanation of detection algorithm. Detection algorithm is not our own. It's by Stenflo and Kosovchuk, 2012. A detailed steps of the algorithm is given in their paper. But briefly, it looks something like this. In the first step, we take a line of sight magnetogram. We correct for the projection effects to obtain the radial component from the line of sight component of the magnetic field. Then what we do is we look for our region of interest, or the strong magnetic field regions on the solar disk, and we check if they satisfy flux balance condition, by which I mean that I will only consider it as a BMR bipolar if both the fluxes, the positive and negative flux, is almost balanced. Then only I consider it as BMR. So if I am identifying it as a BMR, then I draw a box around it and just move. Now we are not yet ready for tracking. One more step is that we have to extract the boundary of the BMR for efficient tracking. So we use morphological operations to extract the boundaries of the BMR, and we also restrict our analysis to less than 0.9 radius of the sun to avoid the projection effects and other like other issues. So it's just to get a clean data, you can say. Now, once this is done, we are ready. We are all set for tracking. And so one good thing about applying the pre-processing step is our detection algorithm. Let me just turn on the pointer. So our detection algorithm will be detecting these two very close lying BMRs as one. But by applying pre-processing step, we can separate it out and we can track them separately. So it's just to compensate any failing of our detection. Now, once that is done, we are getting into tracking. So we are calling our code AutoTAB, that is automatic tracking algorithm for BMRs. So now suppose that this is the BMR that we want to track. What I do first is calculate the time for which this BMR will take to come to the limb. So we know the differential rotation rate. We very well know the differential rotation rate at different latitudes. So we can easily calculate that. And we collect all the binary images. So this is the binary image of this particular magnetogram. So we collect all these binary images of this tracking period. I again repeat, tracking period is the time for which the BMR will take to reach the limb. So in that tracking period, I collect all the binary images. Now, suppose this is at equal to 0 minute, equal to 0. This is our magnetogram, and this is the binary map, and this is the BMR that we are intending to track. Since initially this code is developed for MDI, so which has magnetogram, which has data of 96-minute cadence. So the next observation will be 96 minutes later. So in 96 minutes later, I have the binary map. So then what I do is I differentially rotate the binary map at t equal to 0 with respect to t equal to 96 minutes. Then I check for the overlap between the differentially rotated map and the map at 96 minutes. So if the overlap is greater than 150 pixels, then I consider the BMR as tracked. Otherwise, the BMR is not tracked. Now, we do it for whole of the time period of the tracking period that I call, where we collected all of the binary maps. And consequently, I am not seeing if I'm not seeing the overlap condition satisfied for next 2 days, that means 30 observations, then I increase the tracking threshold, overlapping threshold to 250 pixels to make sure that we are tracking the intended BMR. Now, this is not done for just one BMR. It is done for all the BMRs that are freshly appearing on the solar disk. And we have 12,173 BMRs tracked from 1996 to 2024. So around two solar cycle and a bit. So, but we know that MDI only has data till 2009 and almost 2010. So after that, we need HMI data. So we try to implement our algorithm in HMI too. And for HMI, again, due to our computational constraints, we had to degrade the HMI data from 4K to 4K to 1K, 1K. And we were successfully able to implement the algorithm. The pre-processing steps can be scaled accordingly, but the other yeah, and in HMI again we use 96-minute cadence data only. So when we compared so this is the same BMR in MDI in the overlapping period, so MDI and HMI, and we checked how the flux and Bmax evolved in MDI and HMI. So we see that the trend is matching very well. So we were successful in implementing the algorithm to HMI too. So, and another thing if we are dealing with anything with sunspots, the first thing that has to be kept in mind is that we should be able to produce the beautiful butterfly diagram, and we were able to produce. So each point here and time, this time represents when AutoTAB first detected the BMR. So we were able to produce this beautiful butterfly diagram, and these are the blank spaces are data gaps. So this I know why it is there, but anyone who is working with SDO data, I don't know why this data gap exists. So if it would be very nice if someone could tell me. But yes, so we were able to produce the beautiful butterfly diagram. So coming to the advantage of our AutoTAB. So the major advantage is our tracking algorithm is a standalone algorithm. So you can use different detection methods, and you have to just create the binary map, and then you can track it. And it's fully automatic. There's no need of any human intervention. It's compatible with different data sets. As I told you, pre-processing steps can be scaled accordingly, and tracking algorithm can be used without any changes. It can AutoTAB can also be adapted to track other features if one is interested to do that, but there are disadvantages too. So we are working on it. So first thing to be kept in mind that tracking algorithm is only as good as detection algorithm. Um, one limitation is small BMRs may not be tracked effectively. We are working on that. So if you call me again for another in the seminar, I may be talking about the tracking of the small BMRs, especially ephemeral regions. And AutoTAB has problem with identifying and tracking efficiently the closely lying BMRs. So that is something that we have to really think about and we have to really work on. And AutoTAB loses track of the BMR once it moves to the far side. So incorporating far side magnetogram is something that we are planning to do. So as researchers, we always ask after a project, we always ask what's next. So, what next in case of algorithm is an improved detection algorithm is always necessary. Better noise reduction techniques, better projection correction techniques are needed, and our colleagues, like I think some of my colleagues are already here, so we are working on it. Morphological better. So extracting the boundaries is a tough job. So we have people working on it, and now it is the AutoTAB works with a fixed overlap threshold, that is certain pixels. So we want to make it as a variable overlap threshold. I had plans to do it, but since it's PhD and I have to move on, so I was not. But I plan to come back to it and improve the code that way. The code and the data will be soon released. It is mentioned. Sorry, I forgot to mention here, but it's mentioned in this article. You can check it out. The link will be provided and is provided there, and it will be updated. So we are still working on the data. We have still some more work to do. So it will be published there soon. Now let's come to some science. So yes, so let's do some science now. We started out to use this catalog to check to check the validity of thin flux tube model. So from BMRs and so some popular feature of the BMR tilt is one is tilt distribution. So if so the tilt distribution, we expect it to be Gaussian with a positive mean. And Joyce law, as I told you, as latitude increase, the tilt should increase. But before getting into analysis, we should understand what we are working with. So one thing to note here that all BMRs are not tracked for entirety of their lifetime. There are some BMRs that emerge and decay on the near side of sun. We can see whole of its evolution just as we observe. I am calling it lifetime BMRs. Please keep the lifetime BMRs like that name in your mind. will be needed. But there are also BMRs that come from the far side and evolve on the near side, or emerge on the near side, go to the far side, or emerge and decay on the far side, but has an evolution on the near side. So I am calling this passage BMRs. So most of the BMRs that we are tracking, as you can guess, will fall into passage BMRs. But one thing that we can be sure is mostly the passage BMRs are strong, big BMRs. So these will be less affected by the turbulence and less affected by the surface dynamics. So for the analysis purpose, we will be combining the lifetime and passage BMRs. And again, in this work, we need to assign one physical parameter value to one BMR, since we are taking tracking into account, and we are treating all the BMRs irrespective of their size. We are treating them same. So we have to assign one physical parameter value to one BMR. So how are we going to do that? So suppose that this is the flux evolution of a typical BMR. So it increases and then decays. Now this is the time period greater than 80% of the maximum. That red line represents that. So we assign a single representative value by averaging the values in these time period. So for example, we are mainly interested in this data, in this analysis part, we are mainly interested in maximum magnetic field value of the region, mean magnetic field value of the region, flux measured during of the region, and the tilt. So I take the tilt values or any parameter values in this time period and average them to get a representative. So this is done irrespective of the phase at which BMR. So by which I mean that if it's a passage BMR or a lifetime BMR, I treat it the same. Yeah. And then once that is done, we look at tilt distribution. And here, so there are many ways of assigning tilt. Here, the practice that we have followed is between any tilt measurement will be between plus minus 90 degree. And we have combined the hemispheres. So assuming that there is no asymmetry between the hemisphere, and any strictly hailed region will have a positive tilt. That is the convention that we have followed, and we get the expected tilt distribution. And the previous literature shows 8 degree, roughly mean tilt to be 8 degree. We almost get that. So our tilt distribution changes. And now coming to the Joyce-Slow plot. So the trend between absolute latitude and the tilt, we see that higher latitude regions has a higher tilt. And the Joyce-Slow slope also agrees with the previous studies. So our Joyce-Slow trend also tracks. So it gives you, okay, you can trust the data, you can move ahead. So with that, we come to the purpose of our study, flux tube model. So yes, so there's a thin flux tube which rises towards the photosphere due to magnetic buoyancy. Then there will be tilt produced by the Coriolis force. And now let's look at this empirical relation. So here gamma proportional to sine lambda EM. So lambda EM is the emergence latitude and gamma is the tilt. So this part is basically the Joyce. Now B0 here is the magnetic field at the convection zone. So magnetic field at the convection zone of a BMR forming flux tube. I hope it's clear. It's the magnetic field at the convection zone of a BMR forming flux tube. So there is no way we can measure that. We don't still have a measurement for that. Now phi here is the flux inside the tube. So are we measuring that? Answer is no. We are not measuring the flux inside the flux tube, but we are measuring what is appearing on the photosphere. So it will be an averaged version. So here what this equation means is that, as you know, the first part is Joyce law, and if the magnetic field at the convection zone is strong, then the flux tube will rise quickly, and the Coriolis force will have less time to produce tilt in the BMRs. But also the flux inside the tube is high, then it will the rising flux tube will be much more affected by the drag force, and it will rise slowly, and the Coriolis force will have higher bit more time to tilt the BMRs. So remember, this is simulation results. Here B0 and phi are independent. But when it comes to observation, we can't treat B0 and phi as independent quantities. So next thing that we have to deal with is that what can be the observational signature that we can look for to validate thin flux tube. So one thing that we can look for is first checking the rising flux tube assumption. So if the flux tube supposedly anchored at the convection zone is rising, then as it rises, we will see that the food point separation increases as it rises. So that can be one. Now, if Coriolis force is the reason for the tilted BMRs, then as Coriolis force will be acting below the surface, the BMRs should be emerging with a tilt in accordance with the Joyce. That will be the second. Third thing is flux dependence on the tilt. If we can find any flux dependence on the tilt, then we are in a good position. But in previous studies, they were not able to find any flux dependence with the tilt, and that has been said as a reason to rule out thin flux tube movement. So this is a bit sensitive and part of analysis. So let's see how's it going. So moving to the first observation, that is food point separation. So food point separation. So what I did is I collected all the lifetime BMRs. Let me remind you, lifetime BMRs are the BMRs which we are tracking from its emergence to its decay time. So mostly they are not that strong BMRs, because if it's whole evolution we can track, then it's not that strong. It's moderately strong BMRs. Majorly it's moderately strong BMRs. And I normalize the lifetime of all the BMRs to bring it into a same footing. So when we look at the normalized lifetime and the evolution of the food point separation, what we see is that initially the food point separation increases steadily, and then there's a slow increase and then saturates. So which agrees with our expectation. So we expected that food point separation should increase, but we are seeing an increase, but here we know that in the initial part there's a bit steady increase. So this was previously reported by Shankar et al. In 2019. Now, next thing I checked is that does the trend remain same in all the flux bins? So I separated the BMRs into different flux bins with one order difference in different flux bins, and I see that yes, the trend remains. So majority of the BMR lies in this moderate flux bin, that is 10 raised to 21 to 22 Maxwell, and yes, the trend remains there. Trend remains well. The blue one will be very small regions, mostly ephemeral regions. So the trend is not that prevalent there, but even in higher BMR case, though it is affected by less number of data points, less number of BMRs in this flux bin, but we do see a kind of increase here. Now, we are calling the food point separation. Food point separation is major contribution to food point separation is the longitude separation and latitude separation, delta phi and delta lambda. So the increase that you see here is more prevalent in the evolution of longitude separation. And so we hypothesize that this can be related to tethering of thin flux tube from the convection zone. So previous simulation studies have shown that at some point the thin flux tubes, the flux tubes get tethered from the convection zone. So it is validated in the simulations. But if such a thing happens, then what will we see as a first indication of that on the surface? It will be a sudden increase in the longitude separation. So we hypothesize that this can be the sudden increase. The reason for the sudden increase can be because of the tethering of the foot points from the convection zone. So thin flux tube approximation, I would say, okay, we have some observational support for it. So yay. Now let's go to the Coriolis force as the reason behind the tilted BMRs. So for this, what I did is I collected all of the BMRs in my catalog, which emerged between plus minus 45-degree longitude. And then I plotted joy slope between them. I plotted, I tried to see what's the joy slope trend, if the joy slope trend is evident or not. And I see that joy slope trend is there. I can see the increase. And so this this was agreed by Kosovich's Stenflo in their 2008 FJ letter paper, but we disagree with Shankar et al. on this basis that BMR emerges with the tilt. But here one has to remember that here the BMRs, I have only considered the BMRs that are emerging between plus minus 45-degree longitude, and also I have taken the latitude and tilt that I have taken is the first detection, is at the first detection. So AutoTAB tracks a BMR, say for 15 detections. I have taken only the first entry of it. So the joy slope plot I made is from the first entry of all the BMRs that emerge between plus minus 45-degree longitude. And I see the joy slope trend. But one has to remember that AutoTAB only tracks the BMR when the flux balance condition is satisfied. So that means that the BMRs would have evolved to a mature phase by the time AutoTAB tracks. So that is one drawback that we have. So what I did is we went back in time and checked for some individual cases. So in the previous study by Hannah Shankar, her group says that the BMRs emerge with zero tilt, and they develop a tilt in the later phase of the lifetime. So emergence is also subjective. So when do you call the emergence is also subjective. So we went back in time, check for some few cases. So I selected 12 BMRs from the rising phase from 1996 and 1997, and only selection criteria was that emergence latitude should be between plus minus 30 degree. I selected the BMRs from different flux ranges, and another one was there should be no prominent flux emergence nearby, because if there's a prominent flux emergence nearby, then the newly emerging BMR will be definitely influenced by it. So I selected some isolated BMRs. And so red represents the time from which the AutoTAB has been tracking the BMR, and blue represents the time in which AutoTAB couldn't track. So in that case, we see that, okay, if this is the first signature, then the signature is emerging almost with zero tilt. Now I can show you another BMR whose signature also appeared with a significant tilt, and the tilt evolved as it emerges, as the time progresses. So out of 12 BMRs that I checked, 8 of their signatures emerged with tilt, and others didn't. So again, this is not a statistical confirmation. We my colleague Ram Bahadur, I think he will be attending this meeting. So he will be working on verifying this part of result. And so Coriolis force as a reason for I wouldn't give a yay or na. I would give a may. So but what we believe is that some part of tilt that is observed in BMRs will be the reason behind some part of the tilt that is observed is the Coriolis force. And tilt is a very erratic quantity. It can be severely influenced by the surface dynamics and turbulence. So at least if we are able to identify the flux emergence properly, we can have a confirmation on this. But we believe that some part of tilt that is observed in the BMRs is from Coriolis force. Now coming to the beast, the flux dependence on the tilt. So what I did here is that if you look at this equation, I brought the sine lambda EM that to this side, to the left side. So it will be gamma by sine lambda EM. So this is to remove the tilt, the latitude dependence on the tilt. Now, people who are familiar with Joyce-Low slope, to them, this is not exactly the Joyce-Low slope, but it's an averaged, you can call it an average Joyce-Low slope. And I studied its relationship with the flux. So what I see is that for a lower flux region, I see an increase in the the average Joyce-Low slope, and a potential decrease after 7 into 10 raised to 22 Maxwell for higher flux regions. So from the simulation result, we expected a weak dependence, but what we are seeing is a strong dependence. But one should keep in mind that in the exact simulation result will not be reproduced in observation. That's one thing. And here phi is the flux inside the flux tube. What we are measuring is our average quantity on the photosphere. So though this is a very strong dependence that we see, but any kind of tilt and flux dependence is valid, and that's a good outcome. Now, as I said, here the magnetic field and flux, here they are independent quantities, but we can't consider it as independent quantities. A similar, in case of our analysis, the BMR's magnetic field and flux is related. So higher the flux, higher the maximum magnetic field value. And we see the similar trend in when we look at the Bmax versus gamma 0 bar. So for lower flux region, we see a higher and increasing trend with gamma 0 bar. And for higher flux regions or higher Bmax regions, we see a decrease. Here we see a very clear decrease. So this result is agreeing with Jha et al. 2020, where where they found a similar result without tracking of the BMRs. Now, so flux versus tilt, is it yay? I am not sure of it. Because there's a lot of confusion involved. So I have one more way to check it. So from Joyce-Low slope. So what we are basically looking at is Joyce-Low slope. Gamma 0 bar is a representative of Joyce-Low slope. So if I look at only higher flux BMRs, I should see higher Joyce-Low slope for them. So that's what I did. I collected all the BMRs and I divided them into 3 equal bins. And one thing as you from A to B to C, you will see that flux bins are unequal, but the flux is increasing. So the thing is, the one first thing that we observe is the scatter is decreasing from bin 1 to bin 2 to bin 3. Now, so which says that lower flux regions have a very erratic tilt because they are strong, they are weak BMRs and they will be affected by the turbulence. But as we go higher to higher, stronger, moderate to stronger BMRs, we see a clear joy slope increase. So again, that is a positive note for us, for people who are looking at flux versus tilt. It is, we see some dependence of flux with tilt, though not that we expected, but any kind of dependence we see is a good sign. So I wouldn't say yay truly. I would just decrease the number of question marks and because much more rigorous analysis. So this analysis only involves solar cycle 23 and 24 and part of 25. So both are which are bit weaker cycles and less number of strong big BMRs. So we need a strong cycle with much more richer data and much more rigorous analysis to again confirm this. But we believe that we can provide some observational support to flux tube model. Now, the end of it all, what does this eventually mean? So we propose that there's two dynamics. There is a dynamic interplay of the forces in rising flux tube. So if the magnetic field in the convection zone of a BMR forming flux tube is less, then they will be much more regulated by the drag and Coriolis force. So the magnetic buoyancy will not be strong, and as the flux tube rises, the drag force will try to pull these will slow down the rise, and the Coriolis force will have less time to tilt the BMRs. So these will be the BMRs which will roughly have a maximum magnetic field less than 1.75 volts. But in case of higher flux regions with a stronger magnetic field in the convection zone, will rise quickly, and the Coriolis force will not have enough time to tilt it, and we will call it that magnetic buoyancy dominated region. So this is the whole picture of what is happening in the rising flux tube. So coming to conclusion, we have developed an algorithm, AutoTAB, which can automatically track the BMRs, and we have a catalog of 12,173 BMRs between the period of 1996 to 2023, which individual contains a tracked in which all these BMRs contain tracked information of them. You can find morphological, magnetic, tilt evolution, positional information. All the tracked evolving evolutionary properties are cataloged, and we use this catalog to validate thin flux tube model. We observe that foot point separation is increasing over BMR's lifetime, and we find that statistically BMRs emerge with tilt. At least some part of the BMR tilt that we observe is coming from the Coriolis force. We find dependence of flux with tilt, though not expected from simulation or simulation results, but we do find some convincing dependence of tilt with the flux, and there is a dynamic interplay between drag force and magnetic buoyancy acting on the rising flux tube. So all in all, our analysis lends some support to the thin flux tube model, but a rigorous analysis is still due. So the algorithm is, the details of the algorithm is published in this paper in AbJS in 2023, and in early 2024, we also published the result, the second part of the results which I presented. One can check out these papers and of course write to me. And this is my conclusion. I'll be happy to take any questions if anyone has, and any suggestions or anything.
Yeah, Hello.
Yes.
So yeah, it's a very nice talk, Anu.
Thank
Really
you.
nice work. So I think we have a few questions in the chat
Yeah.
box, so you can check
Okay.
that, or the audience can
Yeah.
unmute themselves and
I
ask
can
you
I can
directly.
I can check. I can check. Hi. Just small suggestion. I think okay, red phones. I also felt that, but yes, I'll shut up. Thank you. I'll take this into consideration. And then
I'm Sneha. It
okay, yeah.
question is a really good talk, by the way. The question is
Thank you.
about probably very initial slides. So you
Okay.
mentioned that to track the BMRs, you decide that if it is tracked or not, you decide that based, yeah, in slide 12, I think you have mentioned it. Yeah, so if the overlap is more than 150 pixels, then then it is tracked, otherwise it's not tracked. And then if it's not tracked, you like increase the threshold to 250 pixels. But is it,
Yes.
or like how do you decide how many pixels it should be? Because if the BMR is smaller in size, like
Yeah.
how many percent of it or something like that, is that the case, or is it a
No. So we started out with trying to accommodate the minimum possible. So this is done by trial and error method, and we try to accommodate even the efficient tracking of even the small BMRs that our detection algorithm could detect. So if you are using a different detection algorithm, I think 150 pixel, like I know that 150 pixels should be tuned, but I am working on an adaptive threshold where this overlap criteria will be decided based on the area of the BMR. So the bigger BMR will have a bigger area threshold, and the lower and smaller BMR will have a smaller overlap threshold. We are working on it. So, so for time being, 150 pixel with this detection algorithm works pretty fine for even for the small BMRs without compromising any faulty tracking of the bigger BMRs. So that's why we do this.
Okay, so this is kind of the like even the criteria is also work in progress.
Yes, yes.
Okay. Yeah.
It's a tedious process, so it takes
I
a
understand.
bit
Yeah,
of
it
time.
must be very difficult. Yes.
So I had to move on at some point, but I'm working on it. That's why we have not published the code yet. So we are still working.
Okay, that's it from my side.
Yeah.
Hi. So whoever has raised their hands or asked questions in the box, so just please unmute and ask questions. Yeah. Yeah.
Chitradeep,
Chitradeep, yeah, he asked questions.
yeah.
Please unmute and ask so that we can also hear. Yeah.
Yeah. Hello, this is
Yeah.
Ashwin. So
Yeah.
I have a quick question. So does your data set also include the rogues and spots? Because if it is tracking the BMRs, then they will also be included, right? Then how
Yes.
did you separate those things?
Yeah. Okay, here in this analysis, we have not tracked we have tracked the rogue sunspot, but we have not separated out the rogue regions. So all the rogue regions and everything is involved. And stay tuned. We are working on a separate. There's a separate that work that will be coming out just considering the rogue sunspots. So just stay tuned.
Yeah,
But
okay.
in this analysis, we have combined all.
Yeah. So and the other thing is you mentioned that where is it? So if you classify the BMRs that are newly generated and those that go around the solar disk and come back again, if you separate them and if you just focused on those that comes around and around the disk and that are like having the journey around the sun, so does those things have more correlation relation when it comes to the Joyce law, because they are weak, right?
Yeah.
And
So
if some of them, yeah, and if some of them have like newly emerged flexing that sunspot, then we can detect it using that too, right? Because like if the correlation is good, that's what I'm. Yeah.
Okay. So one thing is that if a BMR comes around for a second time, right now, since we have not incorporated far side magnetograms, we don't have a way to classify them. So if it's coming from the other side, if it's coming back around for the second time, so so we have to work on that. So and the next thing, so in this analysis, we have considered it as a new BMR if it's come around for the second time. So yeah, and second thing about the flux emergence that you asked, so the tracking takes into account any dynamic evolution of if flux emergence is happening in the active region, the our analysis takes care of it. So we are planning some work with some so as I told you, last 2-3 years I have been just looking at the BMR evolution. So I have got some very interesting active regions with a lot of which can be a separate study altogether. But for this, talking about this analysis, our tracking takes into account this the dynamic evolution or the flux emergence that's happening. That's happening on the lifetime of the BMR. But how much? So it will create the which I again said in my talk also, because the tilt is very scattered. Like there's a significant scatter associated with tilt. As you look at the region, it changes a lot. But we have, for some analysis to be done, we have to move to decide on one point and get on with it. So there can be a lot of other ways to put one parameter value for one BMR. But yeah, this is the way we went for. But we have some works planned looking at in this complicated regions, and yeah, we have some works planned. But right now, this is the way we decided to move forward. But our tracking takes into account the flux emergence.
I forgot to mention that it was a wonderful talk, and I have enjoyed it thoroughly. Yeah. Thank you.
Thank you. Thank you so much.
Hi, Anu. I think his microphone is not working. Sreedevi's microphone is not working.
So I can just read the question. So
thank you. Yeah.
Does your analysis in any way tell about the depth of origination of flux tubes and any indirect empirical estimates? Yeah, so very wonderful question. So when I was doing this analysis, this is something that bothered me also. So thin flux tube assumption is basically from that the flux tubes are anchored at the convection zone. So, but I know there are so many, there are other theories where saying that it may not be even anchored at the depth. So, and we don't, so even in the empirical formula, we don't have much idea about the magnetic, like the thin flux tube forming, BMR forming flux tubes, magnetic field at the convection zone. So I don't have a definite answer to this, but yes, we are trying in some way. We will be trying to decode this, but I right now I do not have an answer to this. We don't have an indirect empirical estimate also for this, but we go ahead with the assumption that it is anchored at the convection zone. The foot points are flux tube is anchored at the convection zone. Yeah.
Yeah, so I myself have a small question.
Sure.
So you showed like the boundaries of the BMRs. So I just wanted to ask that what's the uncertainties on your like boundaries of the BMR, like error bars or uncertainties, selection. Like
yes,
when you
so
select,
if it's I don't have a like error bars in such a way, but you can look at these two. So it also depends on the noise of the magnetogram and how fragmented this is. So So like I agree that the morphological operation is not, it does a decent job. I can say only that, like getting the boundaries of the BMR. Okay, even if you look at this image, I hope you can see my cursor. Even if you look at this image, like the extracting boundaries will be a very difficult. So even when I'm making the binary map, the fragments that goes out is missing here. But when just 96 minutes before, you get a better estimate of it. So it all depends on how the noise level of the magnetogram, and also in a way how many active. So our detection algorithm works on we look for the intense magnetic field region. So how do we decide what is a strong magnetic field region? So if you have if it's in a maximum phase, you have say 10 BMRs. So obviously you will, compared to them, a small BMR or a small ephemeral region will be lost. So our morphological operation is also dependent on how many BMRs are there in that magnitude. So if you are aware with the morphological operation, you use kernels. Kernel is adaptive based on the average magnetic field of the magnetogram. So did it help with your answer?
Yeah. Thank you. Yeah, now we have the idea. I think Shatabdo has a lot of questions. I think so he can unmute and ask. So yeah.
Has he
Okay.
put it in the chat?
I
Then I can
think
check.
no, I think he left, I guess. So okay, so he asked in the first actually
Define a
from
thin
the
flux
beginning.
tube,
So
and how
yeah,
do you tag flux tube as thin compared to any general flux tube?
yes.
So here the thin flux tube assumption is that so actually thin flux tube, I don't think so. It is less it's least affected by turbulence is what Parker coined. It is, that's what his phrase was. But yeah, so yeah, that's how he coins the thin part of it. So the radius should be less than the length scale of the turbulence. So that's how he coined it. So yeah, that would be my answer.
Okay.
Yeah. So you can just consider it as a bunch of magnetic field lines.
But unfortunately, I guess he left, I guess. So
any other questions that I'll be happy.
Yeah, if anyone has any questions, so he or she can just unmute and ask. Anu.
Well, then I have a question that, though I have not much idea, in-depth knowledge on these facts, but what is this binary file of detected BMRs means? What is this file?
So I said binary image. So this is the binary image. Okay. So yeah, the detected regions will be in as ones, and non-detected regions as zeros. And inside the solar system.
Okay, and in the automatic algorithm, what is this automatic part? Can you just define that? I have seen many where you have defined what is the tracking thing and all such, but mainly what is this automatic mainly means in the rhetoric way?
Okay, so so many of the tracking algorithm, that is, so the normal classification and tracking happens it's manually. Many times it's manually. So now and many are semi-automatic, which means that at some point there needs a human intervention. for example, there is work by Jaramillo's group, Andres Munoz Jaramillo. Some people may be aware of him. So he has developed a tracking algorithm where multiple closely lying BMRs have to be the code stops there, and manually we have to separate to tell the code that okay, this is one BMR and this is second BMR. So there will be a human intervention in the running of the code. Here, once you give the binary files, rest code decides, or code takes care of everything, of all the parts of tracking. So there's no need of human intervention, and everything is done automatically. I hope it's clear now.
And so what then consists of in this AutoTAB catalog then?
AutoTAB catalog consists of individual tracked information of right now 12,173 BMRs with its positional information, magnetic information, morphological information. Yeah, and all these three, so that you can derive other quantities.
Okay, and it is from 1996 to 2023.
2023.
2023. Okay. So before that, any BMR was not then what I would say.
So our detection algorithm works with the line of sight magnetograms. So MDI data is from 1996 and till 2010, and after that we are having HMI data, HMI line of sight magnetogram data. But we will be continuously updating our catalog. So that's why we started from 1996, and one can do the detection and tracking with the ground-based ground-based magnetogram that existed before. But this detection algorithm and the tracking algorithm was initially developed for MDI. So that's why we started from 1996.
Okay, thanks for the talk. Great talk also.
Thank you.
Anu,
yeah.
So I have a small final question.
Yes.
So to you. So actually, we are speaking about the drag, the effect of drag on gamma, right? When the BMRs are emerging out. So how do you quantify the drag? Like for the drag, you need the drag coefficient and the velocity.
Yes, yeah. But we don't have any observational. I cannot do it. So that's why I said like it's hypothesis. So we are trying to. This is one of our explanation for why this increase and decrease is happening. So yeah, this is one of the hypotheses. So we don't have yet an observation. So we need something like I really hope heliosysmology pays its way, and we get to have definite measurements. But right now we have to work with what is seen in the footage. So yeah.
But it's really a nice work. Yeah.
Thank you. Any comments you have? I really like. I have a nice audience here, so any comments on improving the work is also very much appreciated. I think I have taken more than my time, stipulated time.
Oh no, it's okay. We have started, I guess, 5 to 6 minutes late, so that's issues.
Well, then just to note that you have said that some weightage was also being classified during the small BMRs. What is this taking, or huge BMRs? What is it taking? Is there weightage thing been in percentage, or have you calculated it in percentage thing?
So I have I told about the weightage thing as a disadvantage of not tracking. So previous literature, previous work have not included the tracking. So every BMR will be like every detection of BMR will be counted as a new BMR. So in that case, the weightage in your statistics, the weightage will be given to a long-living BMR. But in our analysis, we have given a representative value for every track BMR. which means that I am considering all the BMR in the same way. Though it's big, small, different fluxes, anything, I'm considering the same way. So in my analysis, weightage doesn't play a role, but in the other literatures, one has to keep that in mind.
Okay.
So if there is no more questions, there are no more questions, so we can like do an applause for Anu. She has presented a good work. Yeah,
Thank you so much. Nice talking to you, Devesh, like after some time.
Yeah, thank you. Yeah, so I'm stopped recording now.